Hi, my name is Jia Chen, and this is my project two. So in this project, I trained a reinforcement learning agent to solve the lunar lander continuous environment using the TD3 algorithm. I will briefly explain the problem, why I selected TD3, and how I trained the agent, and then the key result lessons I learned. So the problem. The goal of this environment is to land a spacecraft safely on the landing pad. So the space has 8 dimensions, including the lander's position, velocity, angle, and indicators showing whether the landing legs touch the ground. The action space contains 2 continuous controls, one for the main engine and then one for the side booster. So the reward functions encourage the lander to move forward, to move towards line and penalize fuel use. So the environment is considered solved when the agent reach an average reverse of 200 or more over 100 episodes. Because the action space is continuous, so we need an algorithm designed for continuous control. I first implemented DDPG, which is a standard actor-critic algorithm for continuous action space. It was natural baseline, natural choices, because TD3 is actually an improvement of DDPG. However, DDPG shows strong instability during the training. The reward increased at first, but then collapsed around episode 300 and never recovers. And then the final evaluation rewards was only 6.3. Which is far below the threshold. Because of this instability, I switched to DT3. So the DT3 keeps the structure of the DDPG, but it introduced several improvements that specifically addresses the instability problems. With DD3, the agent achieves the mean evaluation like a rewards of 240, around 240, so which successfully solved the environment. Next, for this part, I'm going to talk about the why DT3 is an improvement. So DT3 improves the DDPG with 3 ideas. First is collapsed double queue learning. Instead of using one critic network, the DT3 actually trained 2 critics that use the minimum of their predictions. This introduced the overestimation of Q value. So the second one is delayed policy updates. So the actor network is updated less frequently than the critics. So that actually allows the critics to stabilize a little bit before the actor changes the policy. And the last one is the target policy smoothing. So the noises added to the target actions when computing critic targets. So this smooths the value functions and prevent the policy from exploiting sharp value peaks. So together, all the 3 changes made TD3 significantly more stable than DDPG. So now we are comparing the training performance between the 2 algorithms. DDPG initially improves, but reaches around like episode 300, and then the policy collapses, and then the reverse jobs again. This is basically a very classic instability caused by overestimated Q values. In contrast, TD3 shows much more stable learning. After about like 100 to 200 episodes, the rewards increase sharply once the replay buffer has enough experience. So the rewards then stabilize around like 100 and 150, and then the policy does not collapse. So this is the key advantage of a DT3. And next is the evaluation. So the evaluation result over 100 episode without the noises. DDPG fails to produce a reliable landing policy. So the mean reverse is only 6.3%, and the DT3 has mean reverse around 240, which is well above the soft threshold of 200. And then most of the evaluation episodes fall between 200 and 300 rewards. So meaning the agent can land successfully most of the time. And next, I also run some like experience on the four hyperparameters. The first one is learning rate. So the default is the 3e minus 4, produce the most stable learning. And the second, tau, which controls how fast target networks update. So actually, this one was more sensitive than I expected. The third one is the exploration noise. So too little noises cause the agent to explore less, actually. And the last one is the policy delay, which is one of the most important parameter. So because of updating the actor twice every 2 critics gives the model more stability. So the challenges. Actually, one of the challenge was the bug. I initially forgot to wrap the target Q value computation, and this actually allowed the gradients to follow through the target networks, which destabilized training, even though the code still ran. Another challenge was training time. So each run took about like 1 to 2 hours on my CPU, which made like large hyperparameter searches very difficult. Also, the first 100 episode looks very similar across different configurations, so it's very hard to tell whether this particular run will succeed or not. And lastly, so the lesson I learned from this one will be the first one is the Q value overestimation is the major sources for the instability of the DDPG model algorithm. This is why TD3's twin critics are so important. The second one is policy delay. Actually, is more like a very sensitive hyperparameter that strongly affects stability. Third is debugging the reinforcement learning system can be challenging because most of the time the failure is caused by the poor performance rather than there's a clear error or something. So if I have more time, I would try out soft actor critic, and I also wanted to run like a longer training experiments and also perform multi-state hyperparameter studies. So overall, the TD3 successfully solved the lunar lander continuous environment. The final agent achieved a mean reverse of 240 over 100 episode, which exceeded the solved threshold. So this project actually showed that the TD3 improved the stability of deep reinforcement learning for the continuous control task. And thank you for watching.